Ever find yourself staring at a wall, paintbrush in hand, with absolutely no clue how much paint you actually need to buy? Well, that's an area problem. And by the end of this, you're going to be able to solve it, and a whole lot more with total confidence. So let's jump right in.
Okay, so let's kick things off with a challenge right out of the gate. You see a shape, you've got a task, a real life situation. You know you need math, but where do you even begin? Take this house, for example. To figure out how much paint to get for this wall, you need to know its total area. Now, I know it looks a little complicated, right? But trust me, it's just a simple puzzle, and by the time we're done here, you'll know exactly how to piece it together. All right, so before we can tackle that big puzzle, we got to make sure our toolkit is stocked. We need to be super fast and comfortable with the basic building blocks of all these complex shapes. So let's do a quick fire review.
First up, the absolute basics. You know this one. For a rectangle, it's simply length times width. And a square? Well, that's just a special kind of rectangle, right? So it's just side times side. Easy enough.
Now for the triangle. Here's the key to never forgetting the formula. Just picture it. Any triangle is literally half of a rectangle that you could draw around it. That's why the formula is 1/2 base times height. Once you see it that way, it's impossible to forget.
And rounding out our basic toolkit is the circle. The area here is pi times the radius squared, and that's it. With these three fundamental formulas, we're now geared up to handle almost anything.
Okay, so we've got our tools. But what do we do when we run into those weird composite shapes that aren't a simple square or a circle? Well, that's where our first big strategy comes in. We build them up.
And look, this strategy couldn't be simpler, and it works every single time. First, you just look at the complex shape and you split it into those basic building blocks we just reviewed. Then, you find the area of each individual piece. And finally, you just add them all up. That's it. Let's put this strategy into action with this classic L-shaped figure. At first glance, you might think, hey, there's no single formula for this. And you'd be right, but we don't need one. All we need is our strategy. And here's the magic. Whether you split it vertically or horizontally, you just end up with two simple rectangles. Calculate the area of each, add them together, and boom, you've cracked the code. It's a beautifully simple solution to what looked like a complex problem.
But what if the problem isn't about adding pieces together? What if it's about finding the area of what's left over after something's been taken away? For that, we need a different approach, the art of subtraction.
This is basically the opposite of our last strategy, but it's just as simple. First, you calculate the area of the entire larger shape, just as if nothing were missing. Second, you calculate the area of that smaller cutout piece. And finally, you just subtract the small area from the big one.
Take a look at this. We've got a large rectangle, and it looks like a smaller rectangle was just cut right out of it. We need to find the area of just that shaded blue region. So how do we do it? We use our subtraction strategy.
Just remember this simple mantra. It's the area of the whole minus the area of the whole. So first, we find the area of the big rectangle. That's 10 by 12, so 120. Then the area of the whole, that's 3 by 5, which is 15. Now we just subtract. 120 minus 15 gives us 105. And that is the area of our shaded region.
Okay, so we've learned to find the area, but what if you're given the area and you need to find a missing length? Well, it's time to put on our detective hats and work backwards from the clues. Check out this problem. We know the total area is 48 square centimeters, and we know some of the lengths, but one key dimension is just labeled x. Our job is to figure out the value of x. The secret here isn't some new, complicated formula. It's just basic algebra. We take the formula we already know, area equals length times width, and we just rearrange it. If that's true, then it also has to be true that length equals area divided by width. We can use this to solve for any missing piece of the puzzle. All right, we have officially assembled our toolkit and we have mastered our strategies: addition, subtraction, and working backwards. We are ready. Let's go back to that house we started with and see how everything we've learned applies to the real world. And we're back. Now, do you see it differently? It's not an intimidating house wall anymore, is it? It's a composite shape. It's just a rectangle on the bottom and a triangle on top. So we use our addition strategy. Find the area of the rectangle, find the area of the triangle, and add them together.
Okay, let's break it down. The rectangular part has a base of 15 meters and a height of 10 meters, so its area is 150 square meters. The triangular part on top has that same 15-meter base and a height of 4 meters. Using our formula, 1/2 base times height, we get 30 square meters. Add them together, and the total area is 180 square meters.
Let's try our skills on one more real-world problem. Farmer Martin needs to know the area of this field to figure out how many chickens he can raise, since each one needs 3 square meters of space. Now, this isn't a basic shape, but we know exactly what to do. We can split this field into a simple rectangle in the middle and 2 triangles on either side, and then use our addition strategy. After doing the math, we find out the total area of the field is 945 square meters. So, we just divide that by the 3 square meters each chicken needs, and we get our answer. Farmer Martin can raise 315 chickens. That's a lot of eggs. You see, this is why area is so important. It helps us solve real problems. So there you have it. From basic formulas to composite shapes and real-world applications, you now have the tools to master 2D area. But this opens up a brand new question, doesn't it? We've been living in a flat world. But what happens when these shapes gain a third dimension and become things we can hold? What happens when area becomes volume? Well, we'll save that for next time.